This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 9 of Week 5. Compressors and compression work. A compressor spends shaft work to raise a gas from a low pressure to a high one. We bracket that work between two ideal limits, isothermal at the bottom, isentropic at the top. Then connect the ideal to the real machine through compressor efficiency, and finish with the trick that pushes a real compressor back toward the floor, intercooling. Start with why we carry 3 idealizations. A compressor spends shaft work to raise a gas to higher pressure, and how much work depends on how much heat escapes during the squeeze. Isothermal, perfectly cooled, temperature never rises, needs the least work, but no real machine can cool that fast. Isentropic, reversible and adiabatic, no heat leaves, the gas heats the most, so it costs more work. The real polytropic process sits between them. The key idea, and it's counterintuitive. Removing heat reduces the work, because hot gas resists compression harder. 2 formulas anchor every problem. For an adiabatic compressor, the work per unit mass is simply the enthalpy rise. Cp times the temperature jump from inlet to the isentropic exit. And that exit temperature is fixed by the isentropic relation. The temperature ratio equals the pressure ratio raised to K-1 over K. The isothermal minimum work path drops the temperature rise entirely and uses R times inlet temperature times the natural log of the pressure ratio. Watch the units. Inlet temperature must be absolute, Kelvin or Rankine. The variable table for every compression work problem. Inlet temperature, absolute. Inlet and exit pressure whose ratio is R. The specific heat ratio K and the specific heat Cp come from the property table. From those you solve the isentropic exit temperature, then the ideal work. Compressor efficiency is given, and it carries you from ideal work to actual work. For air, the only 2 constants you bring are Cp and K. Here is the trap that costs the most points. A real compressor always takes more work than the reversible ideal, so efficiency is defined to come out below 1, and that forces the ideal work onto the top. Compressor efficiency is ideal over actual. The ideal is the smaller number. A turbine is the mirror image. Its ideal output is the larger number, so the actual goes on top. The 2 devices use opposite ratios. To get actual work, divide the ideal by efficiency. Dividing by a number below 1 makes it bigger, exactly what a real machine should be. The real process is polytropic. Pressure times volume to the N is constant, with N between 1 and K. Its work formula carries the N over N-1 factor out front. The payoff is one ladder you must memorize. Isothermal, with N equal to 1, is the theoretical minimum. Polytropic is the real partially cooled process. Isentropic, with N equal to K, is the adiabatic reversible limit. Actual is isentropic divided by efficiency, the most work of all. The order never reorders. Better cooling slides N toward 1 and the work toward the isothermal floor. Now the escape from the isentropic ceiling. A single stage at a big pressure ratio overheats the gas and runs near the isentropic limit. Split the compression into stages and cool the gas between them, intercooling, and the path zigzags down toward the isothermal floor. Total work is minimized when every stage carries equal load, which means every stage gets the same pressure ratio, the overall ratio to the 1 over N power. For 2 stages, that optimum intercooler pressure is just the geometric mean of inlet and outlet. Each added stage removes more heat and pushes the total work closer to the isothermal minimum. Worked problem. Air is compressed from 100 kilopascals and 300 Kelvin up to 800 kilopascals, a pressure ratio of 8, at a compressor efficiency of 0.82. Treated as an ideal gas with constant specific heats. Find the ideal isentropic work, the actual work, and the actual exit temperature. The plan? Get the pressure ratio, then the isentropic exit temperature from the property relation, then the ideal work from Cp delta T, then divide by efficiency for actual work, and back out the real exit temperature. Step 1. The ideal work. The pressure ratio is 8. Raise it to the exponent, K-1 over K. which is 0.2857, and you get 1.811. Multiply by the inlet 300 Kelvin, and the isentropic exit temperature is 543 Kelvin. Then, the ideal work is Cp times that temperature rise, 1.005 times 243, about 245 kilojoules per kilogram. That is the least work an adiabatic machine could take to reach 800 kilopascals. Step 2. The actual machine. Divide the ideal work by the efficiency of 0.82, and you get about 298 kilojoules per kilogram. Back out the real exit temperature from the actual enthalpy rise. The temperature climbs 297 Kelvin, landing near 597 Kelvin, about 324 Celsius. Check it both ways. Actual work exceeds the ideal, and the actual exit runs hotter than the isentropic exit. The irreversibilities show up as both extra work and a hotter gas. For contrast, the isothermal floor here is only about 179 kilojoules per kilogram. That big gap is exactly what intercooling would chase down. 4 traps. 1. Inverting the efficiency. For a compressor, efficiency is ideal over actual. Ideal on top because it's smaller, so you divide the ideal by efficiency to get actual work. A turbine flips it. Don't copy it over. 2. Gauge or Celsius temperatures. Every formula here needs absolute temperature. Feeding 27 Celsius instead of 300 Kelvin wrecks the exit temperature. 3. Scrambling the work ladder. Isothermal is the minimum, not the maximum, because removing heat lowers the work. 4. Forgetting why we intercool. Cooling between stages drives the work toward the isothermal floor, and equal stage pressure ratios minimize the total. Bookmark the compressor pages. The isentropic work, Cp times the temperature rise, with the pressure ratio bracket. The isentropic property relation that sets the exit temperature. The compressor efficiency, ideal over actual, ideal on top. The isothermal minimum work with the natural log. And multi-stage, work minimized when every stage pressure ratio is equal. Almost the whole topic sits on 2 facing pages, plus the isentropic relation. You now own the compressor. Bracket the work between the isothermal floor and the isentropic ceiling. Lock the exit temperature with the pressure ratio relation, and divide the ideal by efficiency to reach the real machine. Next, we run the device backward. A turbine drops a hot gas from high to low pressure and extracts work. The same Cp delta T and the same isentropic relation return, but the efficiency flips. A turbine is actual over ideal, actual on top. Carry today's work ladder. It's the backbone of the Brayton and refrigeration cycles still to come. See you in the next topic.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.